Hello there, and welcome to our next lecture here in our series of lectures. Today, up on top is Chapter 5. Chapter 5 deals with early atomic theory and structure. Atoms, very interesting. We're going to talk about them today. Maybe a little bit about electrons, protons, and neutrons. Not to mention a little bit about atomic mass here in this chapter. All right, I think all that's left to do is say enjoy the lecture, and we will throw it over there, way over there, little further, little further. All right, too far. Take it away. Okay, everybody, we're back here for the next chapter up on tap, which looks like it is chapter 5. And in this chapter, we're going to talk about the atom. We're going to talk about some important experiments that led us to a better understanding of the atom. We will then talk about protons, electrons, neutrons, obviously, as we're talking about the atom. We'll talk about atomic number, mass number, and I think we'll finish up this chapter talking about atomic mass. So let us get into this here and talk about sort of the beginning parts of our understanding of the atom itself. And we'll start with Dalton's atomic theory. John Dalton was an interesting guy. He showed unusual talents for math and science at an early age. He kept weather records every day of his life. So he woke up, I guess, and wrote down the weather every day. Never married, surprisingly enough, but he did like to go bowling on Thursdays, and that's a really important thing. I think you should know. Never know where that might show up, so make sure you know it's Thursdays and not like Tuesdays or Fridays or half price Saturdays. He did like to go bowling on Thursdays, but really, besides bowling on Thursdays, one of his most important things was he really did formulate a precise definition of sort of what we call atoms. And let's take a look at sort of Dalton's atomic theory. And here again, we run into a theory like we've discussed in several chapters before. And remember, a theory is something that may not be correct in all aspects of it, or maybe later shown to be incorrect in some aspects of it. And Dalton's atomic theory is no different in that aspect. There's some important points to it, which we're going to go through. And as we'll talk about, there are some points where it was found later on that it may not be so correct. So let's talk about some things here. So he thought elements were composed of these extremely small particles they called atoms. There was this idea that they were sort of indestructible. And that's one of the sort of points of Dalton's atomic theory, which is not really correct. The idea of sort of like nuclear reactions, where you can sort of change one element into something else, sort of makes that idea not so correct in all aspects. Atoms of a given element are identical. They have the same size, the same mass, and same chemical properties. That too is a part of Dalton's atomic theory, which was found not to be so correct. This idea that if you have an atom of iron and all atoms, say, of iron, they're all going to be identical to each other, was found to be laterly not so correct. Also, sort of in the realm of nuclear chemistry, the reason for that is, as we'll also talk about here in this chapter, the sort of idea of isotopes basically disproves that idea. And isotopes, as we'll talk about a little bit later on this chapter, is basically the same element, but they have different masses. So clearly, if they are the same element, but they have different masses, those atoms cannot be identical. There has to be something different about them to give them different masses. So that's not so correct. Atoms of one element are different than atoms of another. That is correct. If you have an iron atom versus a copper atom, for example, those atoms will have very different properties, or definitely some different properties, which really does distinguish them, from one being an iron atom and one being a copper atom. He said that compounds are always composed of atoms of more than one element, and as we've been talking about, that is correct. A chemical reaction basically involves only the separation, combination, and rearrangement of atoms. It does not result in their creation nor destruction. So that is definitely true in chemical reactions, as we've talked about a little bit, I think, and we'll continue to talk about. And that's also the idea of the law of conservation of mass, which says that matter cannot be created nor destroyed. So the idea here is when we have in our chemical reaction our reactants going to our products, remember that essentially the only thing we're going to be doing here is breaking bonds. And on this side, we're going to be making bonds. And really, when you break and make bonds, it really all has to do with electrons. And it may not make sense at this moment, but maybe a few slides down the road here, it may make a little bit more sense. That's a really important distinction here in a chemical reaction is it's really just electrons being involved. And that's really why we do have the conservation of our elements. So, as we look at any type of reaction, say something like this here, what we start with on the left-hand side, if we just add up everything, there's 2 nitrogens, there's 6 hydrogens. And on the right-hand side, this 2 gets distributed, and there are 2 nitrogens and 6 hydrogens. What we start with and what we end with are the same in terms of their elements. We don't lose anybody. We don't create new elements along the way in a chemical reaction. They just get rearranged. So for example, here, basically at the beginning, we have nitrogens attached to each other plus 3 hydrogen gases. And these guys sort of, all these bonds here break. And they get reassembled on their side and actually forms a new compound. And in this case, we get ammonia, which looks something like this. Later on, you'll be able to draw this yourself. We actually have a couple of these guys here. So obviously, as you can see here, beginning in this particular example, all the elements were, basically together, if you will. So we have hydrogens and nitrogens together. And over here, we have a nice combo platter of everybody together. We have our nitrogens and our hydrogens coming together to form these new compounds. So these are the important parts of Dalton's atomic theory. Again, the couple parts that really are not sort of correct. Again, it's the idea of atoms being indivisible, indestructible, and also the idea that all atoms of the same element are identical to each other. Again, the existence of isotopes, which we'll talk a little bit later on here about, sort of disproves that idea. But all the rest of the parts, still correct today. So this is sort of how Dalton pictured a collection of atoms. And again, it kind of goes back a little bit to what we were talking about also in another chapter. Again, we have only certain numbers of elements, a different combination of these elements will give us different compounds, and they'll have some different properties. So here we're really looking at a couple of examples of starting with the elements hydrogen and oxygen, and we're ending with 2 different types, for example, in B and C. They are both still hydrogen and oxygen, but they're different combinations of hydrogen and oxygen. So one makes water, which is the center guy there, H2O, and one makes H2O2, which is hydrogen peroxide. Again, although they're both composed of the same elements, because of the numbers of elements that are present, the type of bonds that are present, they have very, very different sort of properties. Let's get into a little bit about the structure of the atom. Based on Dalton's atomic theory, there were several ideas that were thought about the atom that came about, and really the atom again is thought of as the basic sort of unit of elements that it can come into chemical combination. They're basically the versions of the elements that get together and, make bonds and interact with each other. A lot of investigations from 1850 to about the 20th century demonstrated that although atoms are really small substances, are particles, they're made up of even smaller particles. And these are what are referred to as subatomic particles. And they're made up of these three subatomic particles: electrons, protons, and neutrons. And we're going to talk about each of these sort of individually and talk about the experiments that helped us sort of better understand what they are and where they're found in the atom. But the overall picture here again is protons are positively charged particles. Electrons are negatively charged particles, and neutrons have no charge. So each of these were sort of discovered along the way in sort of understanding the atom. And obviously they're located in different parts in some cases of the atom. So the first sort of particle we're going to really look at is the electron. And a lot of experiments that helped us really better understand the electron really came with the discovery of what is sometimes referred to as the CRT, or sometimes referred to as the cathode ray tube. So we talked about the idea that opposites attract in chemistry. So again, things that are positive and things that are negative, there definitely is an attraction to them, right? And we also talked about the idea that same charges repel one another. So again, if you got a positive thing near a positive thing, not such a good combination. Negative guy near a negative guy, not such a good combination. In these cases, they're going to pretty much head it away from each other as far as they possibly can. So the cathode ray tube is a tube that basically shoots negatively charged particles, like we have here, this little stream of negatively charged particles like electrons. And it also has an electrical sort of field. So there's a negative side and a positive side. And as we were just talking about there, since opposites attract, the negatively charged particles are going to find themselves heading towards the positive side of the electrical field and clearly away from the negative side. They will oftentimes hit this sort of side. A lot of times they'll put a fluorescent type material on there, and that will allow you to kind of see where the particle sort of hits. Now, you may be familiar with a CRT tube. You may even have one in your house, or had one in your house, or seen one on TV, or your TV was one. If you remember, perhaps TVs actually used to have, a really bad drawing here. TVs used to have backs to them, not like very flat screens like we have now. A lot of years ago, TVs, I guess I'll put my little TV window, my knobs on it there. Get some TV antennas going on there. Yes, the TV antenna used to be inside the house, yes, or probably on the roof. But you used to have a TV that actually had a CRT tube in it, and you could take the back off of the TV. You call the TV repairman out. You just wouldn't go to Costco and go buy a new one or anything like that. You would have somebody come and repair your TV. Also, maybe you've seen an older type of computer monitor, probably not the one you're using right now or that you have, but maybe you have one laying around. I still got it, one or so laying around. They're the ones that have kind of the big backs type of computer monitors. It's almost a not bad drawing of one. Those are the ones with those kind of big backs to them. Those used to be referred to as CRT monitors, and those are cathode ray tubes. So new monitors, obviously, flat screen TVs and stuff like that don't have CRT tubes in it. They're basically a little bit different in the way they work. But old TVs and computer monitors used to have them. So, we actually used to use them not too long ago still. So how a cathode ray tube works, as I mentioned, is it will basically shoot those negatively charged particles like electrons from the cathode side is referred to. It will kind of be drawn to the positive side and again allow that stream to pass through. They call that the cathode ray, that kind of stream of negatively charged particles. It would go through there. Like I said before, it would really sort of strike the glass on the other side was coated where you can really see where the beam is basically heading. So the cathode ray tube, which has these negatively charged particles, is really important for obviously the discovery of the electron and really sort of the properties of electrons. And using in general, as we'll talk about in some other experiments as well, using particles that have charges in a lot of cases can be very helpful because of that opposites attract. So let's just take a moment to talk about some particles that are sometimes used to explore these type of experiments. And, there's a few radioactive type particles that are used in a lot of experiments. There are alpha particles. And alpha particles were essentially positively charged radioactive particles. They're really like the helium nucleus. There was also beta particles. Beta particles were basically radioactive particles that were negatively charged. They're basically like an electron. And there's also gamma rays. And gamma rays are basically just pure energy. They have really no charge. So these three sort of particles, along with some other ones that have charges that maybe even don't have charges, are very helpful when you're doing experiments, for example, with electrical fields, which has a positive side and a negative side, or even a magnetic field, which has kind of a north pole, south pole, which works very similar as well. And for example, as we can see here, if we were to shoot a particle through an electrical field, and if we shot a particle, for example, and we shot this particle and we weren't really sure what the charge was maybe on the particle, but we see that it does kind of bend upwards towards the positive part of the electrical field, we would know that it would have the opposite charge of that electrical field, which would be a negatively charged particle. Just like if we shot a particle and basically it kind of like bent towards the negative part of the electrical field or was attracted to the negative part of the electrical field, we would know that that particle was basically a positive particle. And lastly, if we shot a particle and frankly it just went straight as my straight line could draw there ish, and it really wasn't attracted to the positive side or the negative side, we would know that that carries kind of no charge. And that's sort of what we see in this picture. We can see the beam kind of gets folded upwards towards the negative side. That would be more of a positive beam. This guy gets down towards the positive side of the electrical field, would be more negative, and this neutral beam would just kind of go kind of straight through. So a lot of early scientists use a lot of radioactive particles, which have sort of charges associated with them, to be able to really explore the atom and sort of the nature of the atom and what other particles might be present. So again, the cathode ray tube used sort of negative particles, which again could be affected by something like an electrical field or a magnetic field. Okay, so this is a picture of a cathode ray tube, and it would be shooting its negatively charged electrons towards here, and you'll be able to pick up on that kind of coated screen, as you can see there, where the beams would be hitting. So one of the first important sort of experiments that were done by somebody using the CRT tube was one that was done by J.J. Thomson. So J.J. Thomson, which is right there, and there's his cathode ray tube right about there. J.J. Thomson used the cathode ray tube and did a number of experiments. And what he was able to come out of his experiments was the ratio of the electrical charge to mass. So he was basically able to figure out what the charge to mass of an electron was through his experiments. And the value there was minus 1.76 times 10 to the 8 C is a coulomb, is a unit of electrical charge per gram. So electrical charge per gram, basically, which is charge per mass here. So one of the first things that you should remember and know that J.J. Thomson did experiments with the cathode ray tube. He basically was able to come up and determine the charge to mass of an electron. The next sort of big experiment that sort of went with it was one done by Millikan, and Millikan did the oil drop experiment. And much like what the name implies, he took oil droplets and atomized them here into little droplets here. And there was like a little hole in this chamber, and the oil drop would want to fall and gain a charge as it's falling. It had a electrical field in here in the plate, and he was able to basically in this chamber adjust the electrical field in such a way that he was able to basically suspend the oil droplet. So the oil droplet wouldn't fall, wouldn't go up, wouldn't go down. It basically would just stay in one place. And from that, he was able to figure out the actual charge on an electron, which was minus 1.6 times 10 to the minus 19. So two really important experiments here in terms of the electron. We have Thomson, who was able to figure out the charge to mass of an electron using the cathode ray tube. We have Millikan, who was able to use the oil drop experiment to figure out the charge of an electron. So why are these two experiments really important for the electron? Well, frankly, if you look at what they both found, they both have charge in common, which means if we use both of the results of that experiment, we are able to figure out the mass of an electron from those two experiments. So using the results of these two experiments, the first sort of the major finding in terms of an electron was what the mass of an electron was. So doing that math there, taking the charge and dividing it by the charge to mass of an electron, we end up with the mass of an electron here at 9.09 times 10 to the minus 28 grams. So I ask you to think about, is that a large number or a small number? So the question marks really help you think about it, maybe. All right, one more. I know you were asking for one more. We'll put one more. All right, so hopefully, you know, that is a small number. That's a really small number. That is like take the decimal and start rolling that way about 28 places and drop down about 27 zeros. So a very, very small number. So again, the first two things to remember: Thomson CRT tube charged the mass of an electron, followed up by the next sort of important experiment, which was done by Millikan using the oil drop and that chamber with the electrical field, where it was able to really adjust the electrical field to get that oil droplet to be suspended, and from that being able to figure out the charge of an electron, and thus being able to figure out the mass of an electron being 9.09 times 10 to the minus 28 grams. So now that we have sort of the electron sort of figured out and a lot of properties of the electron, the next sort of major discovery or sort of areas of the atom that was sort of explored was really the idea of the proton, and really not thought of originally as in the nucleus, but sort of the nucleus came out as some of the experimentations we're going to talk about here. So let's get into that. So definitely, though, going into these next sort of sets of experiments, there were several things that were sort of thought of about the atom or features of the atom in the early 1900s that was clear. It obviously contained electrons, as through the discovery there, basically, of the cathode ray tube, and again, Millikan's sort of experiment. The other part was that it was believed that the atom was electrically neutral. So the idea and sort of the thinking at this point was, all right, well, we know it has negatively charged electrons. So that must mean in order for it to be neutral, there's got to be something in that atom that is positively charged. So that was sort of the idea that they were thinking about, was got these negative things, got to have something positively there to balance out the charge. So around the turn of the last century, the accepted model for the atom was actually one that was proposed by Thomson. And Thomson basically thought of the atom, as we'll see, maybe a better picture here than what I'm going to draw, but I'll give it the old try, was a sphere of positive charge. So he really felt that the atom had basically all this positive charge really spread out, kind of diffused over the entire atom. He also felt that within this sphere of positive charge, they had electrons that were embedded inside. And he also felt that most of the mass of the atom was made up of these electrons. This was sometimes referred to as the plum pudding model of the atom. Plum pudding is I believe, English dessert, pudding and raisins. So, like the pudding is the positive charge really spread out, and the raisins would obviously be equivalent to the electrons. So this was sort of a accepted model or early model of the atom. Here's a picture similar to the one I just drew there. Again, here, the yellow is all the positive charge. And again, these are all negatively charged electrons embedded inside there. And this was really sort of the accepted model of the atom kind of going forward at this point. And it was believed to be sort of what the atom was basically looking like. Now, this all sort of came to a head with the next sort of really important experiment, and that is the gold foil experiment. So the next kind of major experiment down the road here that you do need to know about is the gold foil experiment. And in the gold foil experiment, was done by a guy named Ernest Rutherford, along with a guy named Geiger. You might have heard of a Geiger counter. That would be him, I believe. Ernst Marsden. They used alpha particles to probe the structure of the atom. So a reminder that we just talked about a second ago, alpha particles. These are our positively charged radioactive particles. So they use these alpha particles to shoot at basically pieces of gold foil and other metals. And they used it with the idea of sort of exploring, what's going on with the positive part of the atom. So if you remember, we kind of used negative particles to explore electrons earlier on with the CRT tube. Here, Rutherford's using positive particles, again, with the assumption that the atom has a positive component that we just talked about. So essentially what they did is they had this idea of the atom, which is the plum pudding model of the atom. Again, we have that positive charge spread out over the entire atom. We have our electrons, again, embedded inside here. So when they shot these alpha particles at these pieces of gold foil atoms, they assumed that these alpha particles would pretty much kind of go through with some deflection. Remember that these alpha particles are positively charged, they're heavy, they're moving really fast. It's sort of the idea of you had like a piece of paper. If you had like a piece of paper like this, and I held one side of the paper and somebody else held the other side of the paper, and he shot like a pin at it or something, it probably would, if that pin was moving really fast, it would be able to puncture through the hole, but there would be a little bit of deflection as it goes through. And again, it is sort of what they envisioned was going to happen. And actually, what they saw happen was something very different than what they sort of imagined happened. And what they saw happen was most of the particles basically went through, when they shot these alpha particles, most of them pretty much had no problem. They went through undeflected, just kind of sailed right through. But they did notice something kind of interesting. They did notice that every so often, boom, we would have these alpha particles bouncing off at these large angles, maybe even heading back to the source of where it came from. So this was very surprising. Like you see here in this sort of picture of the experiment setup, they have their alpha source here. They're shooting it, and essentially the strongest beam, as you can see there, is coming straight through, no problem. But again, every so often, we got these deflected particles coming out at these sort of large angles. So this was very surprising to them. They did not really expect that. They found, as I said, most of the particles penetrated the foil with really no deflection, or was undeflected, or very slightly deflected. But again, every now and then they did see that sort of large scattering of those particles. And because they saw the large scattering of those particles, it was kind of like, again, compared to shooting a gun at a piece of paper and having sort of the bullet bounce back at you, something you would not sort of expect to happen. So that was kind of unexpected. So we want to really think about maybe what's happening here. So first off, if we think about the idea of we have these particles sail right through, no problem. So, if you think about sort of the pen example, if I grab a pen and throw it, and it just goes straight and doesn't move in the path, out of the path that I threw it, it clearly did not hit anything. Yeah. So that was sort of what they had to sort of reckon here was these particles pretty much sailed through some empty space, right? There was nothing in its way. Nothing it hit, because they just went straight through. But when we have these particles that are sailing this way and then starting to bounce off at these really large angles, clearly it had to hit something. So what could have hit? What was really there to get in its way? Well, we also want to think about what we were shooting. We were shooting some alpha particles, which are positively charged particles. So these positively charged particles got bounced off every so often at these really large angles. Remember that opposites attract, but same charge repel one another. So clearly, in order to bounce those particles off, those positively charged particles off in that big direction, it had to hit something very, very positive. So if you think about sort of my example I had earlier, where we had sort of this paper, aka post-it note, I suppose, that this was all the positive charge in the atom. But if we did not have the positive charge sort of spread out all over, and we take the positive charge and fold it, and fold it, and fold it, for example. What's that old saying? You can only fold something maybe 7 times before you can't fold it anymore. But let's just say all the positive charge now is in this very, very concentrated, densely concentrated area. And if I try to shoot my pen through it, it is going to probably hit it and be deflected off. So this was a really sort of important discovery in terms of the structure of the atom, what Rutherford found. Here's sort of a picture of that. Basically, what they expected to happen was there on the left. Again, they sort of expected with the positive charge being spread out all over the atom in the Plum Pudding model, that the alpha particles would be able to kind of go through with some deflection. But what they actually saw was, again, most of them went through with no problem. But again, we had the scattering where it had to hit something very, very positive. So what did this mean? This meant, as we will talk about, we probably need to move away from the Plum Pudding model, because Rutherford's experiment pretty much disproved it, if you will, that that's not really the correct idea of the atom. So Rutherford explained his experiments, but really had to sort of abandon that Plum Pudding model and come up with sort of the current model, if you will, of the atom. And according to Rutherford, he felt that the atom was basically mostly empty space. And again, that is what sort of accounted for all those particles that pretty much sailed through with kind of no problem. He also explained that the atom had to contain a very dense positive core, which was later called the nucleus. And that also accounted for the particles that basically bounce off at these really big spots. So we have our nucleus there at those really large angles. And later on, as we'll talk about, it was discovered that the nucleus contains our protons. And later on, like in 1930s, it was found that it also contains neutrons, basically. Lastly, and really sort of the major departure from the Plum Pudding model was, if you remember, the Plum Pudding model had the idea that most of the atom's mass was made up of those electrons. And it was believed now that actually most of the mass of the atom was made up of the nucleus. So Plum Pudding model, based off of Rutherford's experiment, out the door, out the window. Revisited new model of the atom, where we basically have our nucleus, which has protons and neutrons in it. We have our electrons traveling really in that empty space. As we'll talk about in a later chapter as well, by the way, electrons don't travel in pretty circles around the nucleus. They actually travel fairly randomly about the nucleus, heading in weird and odd ways. They do not travel in pretty circles or anything like that. So again, this idea that we talked about earlier on as well, that, you know, experimentation leads to better understanding of things. And although we sort of think maybe we understand how something is, there could always be some type of experiment down the road that may lead to a new understanding. And that's what happened here. So early experiments really pointed to Thomson's model, the Plum Pudding model, being correct. Definitely sort of disproved here, if you will, by Rutherford's experiment. And again, our new model of the atom. So what do you need to know here from this little part? You clearly need to know the plum pudding model, what came out of it, what it was, and obviously the couple experiments that we previously talked about before. You need to know Dalton's atomic theory, what Thomson did with the CRT tube, Millikan oil drop experiment, the plum pudding model, Rutherford's gold foil experiment. You do need to know what he did, what he thought was going to happen. You also need to know, and really what he discovered happened. And obviously, here you also need to know the kind of new, I won't say new version, the sort of correct version, if you will, of what the atom's makeup is. All right, to finish out a couple more things here about the atom. So here's just sort of a table of a lot of the experiments that helped us understand what is happening with the atom and the major stuff. And most of these is what we just talked about. So kind of a forerunner to the cathode ray tube was gas discharge tubes, which can have negatively charged electrons or positively charged ions. That was sort of a forerunner to the CRT experiments, which kind of focused more on electrons and negatively charged particles. Millikan's experiment we talked about, and obviously Rutherford's experiment. So it's a nice sort of summary slide of some of the experiments that we've talked about up until this point. Now, touching upon protons here, protons again are those positively charged subatomic particles that are found in the nucleus. Experiments basically have determined that the mass of a proton, it was 1.67252 times 10 to the minus 24. If you remember from a few slides back, our friend the electron had a mass of 9.09 times 10 to the minus 28 grams. Minus 28 means 28 places that way in a small number. Minus 24 means only 24 places that way. That means that actually the proton is, as it says here, about 1,840 times heavier than any electron. So this is really important as well because, again, it basically shows that Rutherford's idea that most of the mass of the atom is actually the nucleus, because once again, in the nucleus, we have our protons and our neutrons in our nucleus. We have our electrons on the outside. So the proton in here, every proton is about 1,840 times heavier than an electron. So that also very nicely sort of backs up, if you will, the idea that it's really not the electrons as most of the mass of the atom, like the plum pudding model was sort of suggesting, but it's actually the nucleus. At this stage, scientists perceive the atom as follows. The nucleus is comprised of most of the mass of the atom, but actually occupies about 1 over 10 to the 13th the volume of the atom. You could think of the atom as the size of the Superdome. If you're not familiar with the Superdome, it's a football stadium there in Louisiana. So like a big football stadium, if you will. I guess we have SoFi out here in LA. But it's sort of like a big football stadium. And you can think of that as the atom. And a small marble on the field, maybe like the 50-yard line, is like the nucleus. So although it is most of the mass of the atom, it does make up a very small volume of the actual atom. Again, protons are confined to the nucleus. We have electrons flying around and about in that empty space outside the nucleus. So is there going to be some attraction between the nucleus, which really at this stage of the game we know has protons in it, and electrons, which are obviously negatively charged? And the answer, hopefully, that you are saying to yourself is yes, because again, here we have that opposites attraction that's happening. And there is definitely some attraction between electrons that are flying around that empty space and the positively charged nucleus. And as we'll talk about in later chapters, depending on where those electrons are, their sort of proximity, if you will, to the nucleus will depend on whether or not they will be involved in things like bonding or not be involved in bonding. There are certain electrons that are really close to the nucleus, which are very much attracted to it. And there are some electrons that are farther away from the nucleus, which are still attracted to the nucleus, but not held as tightly. And as we'll talk about in a later chapter, those are what are referred to as valence electrons, and those are the ones that are involved in bonding. So they're also, by the way, this attraction between any of the electrons and the nucleus is essentially what keeps the electrons from, if you will, just flying off, right? They're sort of tied to the atom through their attraction to the nucleus. Again, as we'll talk about in a later chapter, some electrons, based on their proximity to the nucleus, will be more strongly attracted than some electrons that are further away from the nucleus. But although at this point, there was protons understood, there was electrons, there was always this idea and thought that there was some other particle that was present. And that other particle is basically the neutron, as we see here. Don't want to ruin the ending, but the neutron. And let's talk a little about how the neutron sort of came about. And relatively speaking, not extremely a long time ago, less than 100 years ago, Rutherford and others have really thought that there definitely was some other particle present. And it wasn't until about 1932 that a guy by the name of Chadwick did some experiments. He shot at thin pieces of beryllium with alpha particles, and what he saw sort of come off of it was these radioactive particles that resembled gamma rays. So once again, as we talked about earlier, these gamma rays were those radioactive particles, or really rays that have no charge. So later experiments showed that these neutral particles had a mass of 1.67495 times 10 to the minus 24. These particles were named neutrons. So the discovery of neutrons and their location basically puts them in the nucleus. And again, we have our electron flying about at some distance. So when we think about protons, electrons, and neutrons, it is actually the neutron, which is why it goes out this many digits. So if you go back, and we'll see it on the next slide as well, and look at the mass that we found for our proton, the neutron just barely beats it out. It is actually the heaviest of all three of those particles. The electron's actually the lightest of all three of those particles, with the proton being very close to the neutron. So if you remember, the proton was about 1,840 times heavier than any electron. And since the neutron is just slightly heavier, it also would be in that ballpark, about 1,840 some odd times heavier than an electron. This also, again, reinforces the idea of we have both the proton and the neutron in the nucleus, and both of those particles individually are about 1,840 times heavier than any electron that is flying around in the atom. So again, that reinforces the idea that was thought, that most of the mass of the atom is actually made up of the nucleus, which contains basically the heaviest two of the three particles that make up an actual atom. Here is a table from your book there of our three particles. And again, you can see our electron to the minus 28 and our neutron, again, just barely beating out the proton. Again, got to take it to several decimal places, but just slightly beating it out. So this, and this, you don't necessarily have to know the exact numbers. They might even be provided for you. But you do need to know that the neutron is the heaviest, followed very closely by the proton, and also the electron is the lightest of those three particles. You need to know their charges. So electrons -1, protons +1, no charge there for our neutrons. And obviously at this point, you should also know where they are found in the atom. All right, so let's talk a little bit about modern concepts of the atomic structure. This is a sort of cross section, if you will, of sort of the idea of the atom. Again, we have our very small volume that is our nucleus here with our protons and our neutrons. This sort of, this is yellowish in this picture, smear is basically that empty space. And this is sort of where we expect our electrons to be randomly kind of flying around in. You can probably make it out here on the screen, but again, this darker area of that sort of, erase all my scribble there. This sort of darker area of yellowish, I guess, or orange type color indicates a much higher probability, as we'll talk about in a later chapter, of finding an electron. And as you kind of fan out, you can see that the color gets lighter and lighter, and these are becoming a lower and lower probability of finding electrons in that particular area. And that makes sense if you think about it. Kind of the darkest color of that empty space where we would have a high probability of finding electrons is near the positively charged nucleus, right? So that sort of makes sense based on what we were talking about. Sometimes referred to as the electron cloud. So let's talk a little bit about the chemistry of atoms. And in normal chemical reactions, as we've touched upon, pretty much it's all about that making and breaking of bonds, and that's all about electrons. So the chemistry of atoms really comes from electrons. They're involved when atoms get together. Maybe just think about sort of the structure of the atom that we just talked about. We have our nucleus, and then we have these electrons on the outside. We have our nucleus and electrons on the outside. And so when a couple of atoms come together, it's probably the first things that come in contact with each other, which are the electrons. So they're the basis of bonds, both types of bonds that we'll talk about in this class. Covalent bonding, where we have electrons being shared. Also ionic bonding, where we have electrons being transferred. Those guys within the nucleus, the protons and the neutrons under normal chemical reactions, are not involved. The only time that protons and neutrons basically get involved is in nuclear reactions, which we don't talk about, I believe, in this class. So under normal chemical reactions, it's all about the electrons. Nothing in the nucleus changes. Just those electrons interacting with one another changes. Hello there. I thought I would just pop in and give you a few reminders about the lecture so far. At this point, you do need to know about Thomson and his experiments with the CRT tube. In addition, our good friend Millikan and his oil drop experiment and what came out of those two experiments. Also, you need to know about the early model of the atom and proposed by Thomson, referred to as the Plum Pudding model of the atom. In addition, what happened with Rutherford and his gold foil experiment and how that drastically changed the idea of the atom. Finally, you need to make sure that you know where electrons, protons, and neutrons are found in the atom. All right, off to the next part of this lecture. It should go this way. Bye-bye. So let's talk about some other properties here of atoms, which are important, and that's atomic number, mass number, and isotopes. So we're going to start with the atomic number. The atomic number, which is sometimes abbreviated with a Z, is the number of protons there are in the nucleus of an atom for a particular element. So the protons are the positively charged guys, and that means that if you have a neutral atom, remember that a neutral atom has no charge. So if you have a neutral atom, the atomic number, which is the number of protons, will tell you also the number of electrons you have to have. So remember that basically the atom is made up of protons, which are positively charged, electrons, which are negatively charged, and neutrons, which have no charge. By the way, all atoms have protons, electrons, and neutrons. The only exception is hydrogen. Hydrogen has no neutrons. So hydrogen has an electron, it has a proton, it does not have a neutron. All other elements pretty much have all three of those things: protons, electrons, and neutrons. So if we think about it, atomic number tells us the number of protons. In order for this thing to be neutral, you would need the exact same number of electrons, right? All the positives equal all the negatives, and everything cancels out. Now, the chemical identity of an atom can actually be determined by the atomic number. So where can we find the atomic number? Well, that is our good friend, the periodic table. And if we go to the periodic table, for example, here and look at nitrogen, we will see lucky number 7 up there on top. And that is the atomic number. So the atomic number can be found in the periodic table. Is usually the number right above the symbol. Might not be directly above it, but it's usually on above it somewhere, either to the left, to the right. But in a lot of cases, it's that number directly above it is the atomic number. So when we look at the periodic table, we see 7 there for nitrogen. What that means is if I have a neutral nitrogen atom, it should have 7 protons. And that means it would also have 7 electrons. So 7 positives and 7 negatives will give me no charge overall, which is, again, why it would be neutral. It has nothing written there. It has no charge. If we look at the periodic table and we find boron, which is number 5 there, we will see the number 5 up there. That means that boron should have 5 protons, which are positively charged. And in order for it to be neutral with no charge, it should have a matching set of 5 electrons. So 5 positives and 5 negatives give us our no charge. If you take a gander at a periodic table that you might have near you, and you look at all the elements there, and you look at the atomic number there on the periodic table, you will see that, frankly, if you run this way, and keep going on the periodic table, there is not one atomic number that repeats. So the most important subatomic particle to know what element you're dealing with is the protons. The protons, which is the atomic number, tells you what element you're dealing with. You will never find a nitrogen atom with an atomic number of 11. And that is because if you go to the periodic table, lucky number 11 there is sodium. So if you know the atomic number, which basically means you do know the number of protons, all you need is a periodic table and you'll know what element you're talking about. Opposite of that is if you know the element you're talking about or dealing with, you could go to the periodic table and you could find its atomic number and you would know how many protons it has. Now, a little note here to keep in mind and is very important is the atomic number definition is just the protons. Although second to that, it will also tell you the number of electrons in a neutral atom. The actual definition of atomic number, and if you are asked the question of what is the definition of the atomic number, it is only the number of protons. Okay. So sometimes people kind of get those things sort of wrapped together. It is true that if you have a neutral atom, it will also tell you the number of electrons, but that is not the definition of the atomic number. It's just the protons. And we'll talk about a case here in a sec where electrons could be different. So if you're asked that question, sometimes people miss it because they're used to sort of autopilot of, oh, atomic numbers, number of protons also tells me the number of electrons. So that must be the definition as well. So once again, atomic number, only number of protons. Let's talk about the next sort of important number, which is mass number. And the mass number is the actual number of protons and neutrons that you find in an atom. So we have our mass number, which is sometimes abbreviated with an A, which is our number of protons and our number of neutrons. We also have, as we just talked about on the previous slide there, our atomic number, which is our number of protons. And if we take both of these numbers together, not really add, subtract, the protons will cancel, and that will give us the number of neutrons. So if you take the mass number and you subtract it from the atomic number, that is how you will be able to find the number of neutrons that you have in an atom. As I mentioned a second ago, except for hydrogen, which only has a proton and an electron, all other elements will have both protons, electrons, and neutrons. Now, there's a really important couple of things about the mass number that people very often, for lack of a better word, screw up on. And that is the idea of, where you find the mass number, what is the mass number, or how you get it. How you calculate the mass number, or the number of neutrons, is how I just showed you there. Mass number is atomic number. When you calculate something like the mass number, the atomic number, the number of protons, electrons, and neutrons, they all should be positive whole numbers. That's really important. So the double jeopardy question here of the day is, I'm going to go to the periodic table here. Going to do my artist rendition here of what you would see on a square. So we clearly just saw that guy right about there is our atomic number. So can you find the mass number on the periodic table? So take a moment and think. Can you find it? The answer is no, you cannot. This number right here, which might be what you're pointing to, I don't know if you're pointing or not, but maybe you are pointing, is not, and I repeat, not the mass number. That is, as we'll talk about a few slides down the road, what is known as the atomic mass, which once again is not the mass number. How do I know it's not the mass number? Well, that's carbon, for example. If we take a look at something like calcium, we'll see something like 4008. If we look at something like hydrogen, 1.008. So once again, if we look at all these numbers, they pretty much are not all caps. That's like yelling I hear these days. Not whole numbers. And what do they all need to be when you calculate something like mass number, atomic number, protons, electrons, and neutrons? They need to be whole numbers. So that's a really good way to remember that, is all those things, protons, electrons, neutrons, need to be whole numbers. Mass number, atomic number needs to be whole numbers. You won't find one. So do not be the person that writes that number down for the mass number unless you're looking for an X, which you probably are not looking for on your exam or quiz. So why do people do that? It's really very common, and it happens a lot. And it does make sense, if you will, because oftentimes, or in a lot of situations, the number you see on the periodic table is often very close to the mass number. So people just think, oh, well, maybe the mass number is just like the rounded version of what you see on the periodic table there. And it's not. There's semi-based similar on this things like how many protons, electrons, and neutrons there are, but that is not, again, how you find it. So atomic number, yes, you find that on the periodic table. Mass number, no. If you need to figure out how many neutrons you have, mass number minus atomic number, you will have enough information given to you in these type of problems where, you'll be able to figure out how many neutrons you have, or maybe you'll be given the neutrons and be able to figure out the mass number from that. So just keep that in mind. Only the atomic number found on the periodic table. Now, isotopes are, again, one of those things that were sort of discovered, as we talked about, that sort of disproved in a way parts of Dalton's atomic theory. And that was the part of Dalton's atomic theory where he said that atoms of the same element are identical to each other. So again, these isotopes, which basically have the same element, but have a different mass. So what does that mean? It means that basically they have different numbers of neutrons. So isotopes basically have the same number of protons, but different numbers of neutrons. And as we just talked about, it is the protons that are most important in terms of what element you're dealing with. So they have to have the same number of protons. Otherwise, there would be different elements. So because the protons can't change, it's actually the neutrons that make up basically the mass difference that we see in isotopes. So hydrogen, for example, has one proton and no neutrons. Deuterium, which is sometimes referred to as heavy hydrogen, has one proton and one neutron. And tritium, which is kind of like the radioactive version of hydrogen, has one proton and two neutrons. So one way that we write isotope is we use the symbol. And on the top left of the symbol, we write the mass number, which is our number of protons plus our number of neutrons. On the bottom left there, we go atomic number, which is our number of protons. So if we were to write our symbols for each of these isotopes, and maybe we weren't sure what the symbol was, I know that it has one proton, which is its atomic number. I would go to the periodic table and I would find lucky number 1, and I would see that H is the symbol that I need here. The atomic number, which is the number of protons, goes bottom left. Remember that the mass number is protons plus neutrons, which in this case is 1 plus 0, which is 1, which means 1 up on top. So again, mass number and atomic number. So how do I find the number of neutrons? You take the top number and you minus it from the bottom number. 1 minus 1 is 0 neutrons, right? Now, if I do deuterium, and maybe this name doesn't scream hydrogen to you, but it does have one proton. So once again, I'm going to go back to the periodic table, find number 1. And again, I see it is hydrogen as well. So we would still use the H for the symbol. Still has the same atomic number because it is still hydrogen. But in this case, for our mass number, adding our protons and neutrons together, that is 1 plus 1 is 2, I believe. So that's going to be a 2 up on top. And again, our number of neutrons, in this case, top number minus bottom number, gives us 1 neutron. And lastly, tritium, which once again may not scream to you hydrogen, but when you see that it does have 1 proton, that again tells us when we go to the periodic table here and find number 1, it is this symbol H, and that means it's still hydrogen. Again, looking at our mass number, that is 1 plus 2, which is 3 in this case, right? And that gives us our mass number of 3. So our neutrons, once again, 3 minus 1 is 2 neutrons in this case. So although they have 3 different names, hydrogen, deuterium, and tritium, they are all hydrogen because they all have 1 proton. And they are all isotopes of each other because of that. Now, this is a very common way that you write mass number and atomic number. Sometimes when people write isotopes as well, for example, they will do something like Cu64, for example. That's, by the way, red copper 64. So what does the 64 number mean? Well, if I go to the periodic table and I look up copper, I am going to find number 29er, I think there. So clearly looking at the periodic table, I'm going to see that this top number is actually my atomic number, right? Because that is the number that you can find on the periodic table. So clearly here, 64 is not the atomic number. You might be able to figure it out. It is going to be the mass number. So sometimes isotopes are written that way. If we were to turn this into our symbol, 29 would go on the bottom, which is our atomic number. 64 would go up on top, which is our mass number. And that means if we wanted to figure out for this particular example, the number of protons would equal 29 in this case, because that is the atomic number. This thing right here has nothing written in the upper right corner, which basically tells us it is neutral. So as we've been talking about, that means that I need to have a equal number of negatively charged electrons, which gives me an overall charge of 0. And lastly, the number of neutrons in this case would be my mass number, which is 64 in this example, minus my atomic number, which is 29. And I'm going to grab the handy dandy calculator and give it a go here. It's going to be a 64 minus a 29. I think I see 35 on the screen there, so we'll go with that. 35 neutrons. So a couple of different ways you could write sort of the symbols for isotopes. I would say most commonly in books, this way it's going to be, but people still do write isotopes very commonly this way as well. So again, if you see sort of the symbol dash a number, that's going to be your mass number. And again, if you see it written with 2 numbers on the left of the symbol, top number should be mass number, bottom number should be atomic number. All right, so why don't you try these examples here? We're looking for the numbers of protons, electrons, and neutrons in each of the following. So take a few minutes and see what you come up with. So let's see how you're doing. So first off, CO is our element, cobalt. Once again here, written this way, top number going to be our mass number, which again is our protons plus our neutrons. Bottom number here going to be our atomic number, which is our protons. So let's take a look here. Here on cobalt, our protons. Number of protons would be equal to our atomic number, which is 27. Once again, there is nothing written here, which tells us it is neutral, and it needs to have a matching set of electrons. Once again, that is going to give us 0 for an overall charge. Our number of neutrons going to be our mass number, which is 60 in this case, minus our atomic number, which is 27. And again, if we take 60 minus our 27, 33 looks like a winner here. And it's going to have 33 neutrons. Taking a look at the next one, which is chlorine. And once again, we see no charge, so it is neutral. Bottom number first is going to help us with our number of protons, which in this case would be 17. Once again, because of the no charge, we should have an equal number of electrons. There we go. And that's going to be 17. Once again, adding those together, no charge overall. Now our neutrons, just like above, we're going to do mass number, which is 37 in this case, minus 17. Gonna shoot us a 20, looks like, for our neutrons. And lastly, U, which is uranium, right there is 0 or no charge. So we're going to look at the atomic number, which is our bottom. So our number of protons in this case would be 92 positive guys. To match that out to give us no charge, we will need 92 electrons. And once again here, our number of neutrons is going to be our mass number, which is 238, minus our atomic number, which is 92. That feels like a lot there. $1.46 maybe. Let me double check here. 146 in terms of our numbers of neutrons. So again, hopefully you can see here, I just kind of want to go through protons probably first. That'll help you get to their electrons and then obviously to your neutrons. Take a look at a few more examples here. So for each of these here, you might want to grab a periodic table. It might be helpful as well. We want to write the symbol with both the mass number and the atomic number present for each of these. So once you take a moment and see what you come up with here. Okay, so again, your periodic table here, probably very helpful. So hopefully you've had it out and you're using it. Should be one somewhere in your book, or hopefully you have one laying around. You know, everybody has some periodic tables laying around or hanging on the wall. Who knows how you decorate? You never know. But we'll start with krypton. So krypton there on the periodic table, if we find it, has the symbol of Kr. Other important information we could pull off the periodic table. It's got like a 36 there up on top, which we know is our atomic number. All right, so we got most of the stuff that we need here. We could start with our symbol, which is Kr. We're going to lay our 36, which is our atomic number there on the bottom. This has got 48 neutrons. So the atomic number 36 tells us that the number of protons in this case is 36. That means that our number of neutrons in this case is 48, which was given to us. And that also means that all we have to do to find the mass number here is going to add those two together, 36 and 48, going to be an 84 happening here. Or a number of, not number, but I guess our mass number would be what I want right there. And that should go top left. Looking at the next one, which is nitrogen. So once again, if you went to periodic table like we drew a second ago, you will see something like this. Once again, there, the top number of 7 going to be helpful as that's our atomic number. So we could start with that. That atomic number also obviously tells us our number of protons, which is 7. And we're going to add that our number of neutrons, which was given to us here. And try without the calculator and go with a lucky number 13 maybe. And a 13 should go up on top. By the way, in this sort of situation here, you could pretty safely assume that they're neutral. There was no mention of a krypton, say ion, or a nitrogen ion, or anything about ions, which are things that have charges, as we talked about in a previous chapter. So you could safely assume in this case that it is neutral, unless it mentions something like it's an ion or this guy has a charge or something like that. Otherwise, again, pretty safe to assume that it's going to be a neutral. So in this case here, we're looking for iron. And if you go to the periodic table, you will find iron at number 26. Something like that. And once again, that's going to be our atomic number there. So iron here would be 26 on the bottom. In this particular case, they gave us the mass number, which is 56. So the atomic number there is going to tell us our number of protons, which is 26. In this case, we're assuming it's neutral, so it does need to have a matching number of electrons, which again gives us 0. And lastly, our number of neutrons will be our atomic number, which is 56 minus 26. That looks like a 30 going on there. So you do need to be able to figure out protons, electrons, and neutrons, the mass number, atomic number, write the symbols with the mass number, atomic number on them. Why we're talking about this, and we kind of touched upon ions and mentioned ions as well, let's talk about what happens when something gets a charge. And earlier we talked about ions. And again, a reminder that ions are things that have charges. And there's cations, which are positively charged. And there's anions, which are negatively charged. So let's just take a couple of these examples here that we just did. Let's do a nitrogen with a -3 charge. And it still has the mass number 13 and the atomic number is 7. So when we look at this, the number of protons in this case will be 7. By the way, the number of neutrons in this case will still be the same, 13 minus 7, which would be 6. Now, in our original guy over here, we had for our protons 7, and we would have a matching number of electrons, which are negative. Would give us 0 charge, which is what we have going on there. So we also know, by the way, from our conversations that when something gets a charge, the protons can't change. And the protons can't change because remember, the protons are the ones that determine what element you're dealing with. So if you change the protons from 7 in this example, you're no longer talking about nitrogen. So clearly the protons can't change, otherwise the element changes. Neutrons can't affect the charge because frankly, they have no charge. So it is, as you imagine, and I think we might have touched upon earlier as well, it is actually the electrons that change. So in this particular case, the number of electrons would actually be 10 electrons. So that means I have 10 negatives plus 7 positives leaves me a -3 left over when I add those together. And that -3, once again, is where the charge comes from. This is an anion, which is negatively charged, and it is made by gaining electrons, as we talked about, and as we see here, actually. So if we look once again at the neutral nitrogen, it's got 7 electrons. The nitrogen with a -3 charge has 10 electrons. The minus charge again tells you that it has gained electrons. The charge number tells you basically how many electrons it gained. So negative means gains, and that is how many it gained from the neutral atom. And again, that's basically the difference, right? 10 electrons versus 7 electrons, difference is 3. So if you have something with a charge and you know how many protons it has, and it has a negative charge, you basically just need to add that much to the atomic number, and you'll have the right number of electrons. So what I mean by that, the atomic number for nitrogen is 7, that's 7 protons. -3 means it gained 3 electrons. 7 and 3 is 10 electrons in this particular case. So let's take a look at something that's maybe positive, like over here. We'll go over here, I think. We'll do the exact same guy here, but we'll give it a +2 charge, 56 and 26 in this case. So number of protons here for our iron going to be 26 to match the atomic number. Our number of neutrons here will be the same as what we had previously, 56 minus 26, which is 30. Now our number of electrons, which is what's going to affect the charge. In this case, it will actually be 24 electrons. If I take 26 positive things and add it to 24 negative things, that leaves me a net of a positive 2 charge, which is where the positive 2 comes from. And what happens here is that's a positive guy, and that is made by losing electrons, which is a cation. And we see that if we compare the neutral guy, it has 26 electrons. Our guy with a positive 2 charge has 24. Once again, the actual charge tells us something. The positive tells us we have lost electrons, and the number is how many we lost from the neutral. And again, neutral had 26, plus 2 means we lost 2, which is 24 in this case. So you could do kind of the same thing if you're not sure. You have a charge and you know the atomic number, which you should. If you know what element you're dealing with, you can just go to the periodic table. So for example, here, if you had iron with a plus 2, you go to the periodic table and see that the atomic number is 26, plus 2, plus means lost electrons, and take 2 off of it. And basically take 26 minus 2 is 24. And again, we're doing that because in a neutral situation, the protons and electrons would be the same. So if you're starting with neutral, it'll be the same number of electrons as your atomic number. And you could just either add or subtract to it depending on the either if it's a positive or negative charge. So why don't you try a couple here? Why don't you do Ni4 plus, and why don't you do O2 minus? In case you don't have a periodic table on you, if you look at the periodic table for nickel, nickel is 28, which is Ni. And oxygen there, in case you don't have a periodic table, it's 8. All right, so take a moment here. Let's go with the number of protons, number of electrons, and number of neutrons in each of these. Okay, let's take a look. Just kind of erase some of the stuff here, get a little bit more room. We'll start with the nickel here. I'm sorry, I guess let's not start yet. Let me actually give you some other numbers, which will probably be a little bit helpful here. Nickel. Do 58 up on top, and we'll do 18 up here. All right, taking another a couple of minutes here. I guess that'd be helpful to have those numbers given to you, I suppose. Okay, let's take a look. So we got these top numbers, which are our mass numbers given to you. We could obviously, if the bottom numbers there weren't given to you, we could go to the periodic table and grab our atomic numbers off of it, and we'll fill them in here at 28 and 8. There we go. 8. All right, so we'll start with nickel now here. So starting with our atomic number, our number of protons in this case would be 28 there. For neutrons would be 58 minus 28. That's going to be a 30, it looks like. And now we're at our number of electrons, which is really what affects the charge of it. So let's just analyze the charge. I got positive, which means it's going to lose electrons. And it's a 4, which means it's going to lose 4 electrons. So really, I could just subtract 4 from the atomic number, and that's going to give me a 24 electrons. That's going to give me a net plus 4 charge, which once again is the +4 charge that we see there. Looking at the other one there, we got looking at our atomic number here, means our number of protons going to be 8. Our number of neutrons here will be 18 minus 8, which would be 10 in this case. And now it's our electrons, which affects the charge. So we can do our analyzing here. I see negative, which means it has gained electrons. And it has a 2, which means it has 2 more electrons that it started with in its neutral state. Looking at its atomic number, which is 8, having 2 more electrons means it basically just going to add 2 to that, which would be 10. Now when we add those together, 10 negatives and 8 positive, leaving me a -2 left over, which once again is where the charge comes from. So that is what you deal with, or how you deal with ions and protons, electrons, and neutrons. It is only the electrons that change, as we talked about again. Protons can't change, otherwise you change the element, which you don't want to do. So you just change the electrons. All right, so adding to our list of what you should know how to figure out protons, electrons, and neutrons in something that has a charge as well. Continuing on here with isotopes, as we talked about, isotopes pretty much work the same way. And that's because, again, the property of the elements are really determined by the protons and electrons in an atom. So the nice thing about it is neutrons really don't participate in normal chemical reactions, which means isotopes have different numbers of neutrons. So it's not going to make a big effect. So one isotope of an element will basically behave and have the same sort of chemistry as the other isotopes. One way where people sometimes take advantage of this, for example, is in the laboratory, they may use a radioactive version of a particular element. And the nice thing about the radioactive version of that particular element is, say, if you're trying to follow, for example, like copper in the body, you could use a radioactive version of copper, and you could basically simulate where the copper goes. And you could follow along where the copper goes by just following the radioactivity. I used to do experiments with radioactive copper, and it works the same way as non-radioactive copper. But sort of the advantage in a research sort of situation is you're able to really determine sort of where the copper ends up, where it goes, for example, by just following the radioactivity associated with it. So it's used also in medicine as well to do imaging and so forth. So a lot of isotopes of elements are radioactive, or they have sort of radioactive parts to them, and they can be very useful in those sort of applications. The last thing we're going to talk about in this chapter is our other number that we actually see on the periodic table. So earlier we were talking about the idea that although we can find the atomic number there on the periodic table, which is our top number, our atomic number, the bottom number is not the mass number, it is the atomic mass. And because, for example, an atom is very, very small, it makes it really hard if you wanted to just pick up one single atom, for example, and throw it down on a scale or a balance. It's probably not going to happen. So a lot of times what happens in chemistry or in science in general is when they have a situation where it's very hard to directly measure something, a lot of times they'll pick something to use as a standard to compare everybody else to. And for atomic mass, it's actually an isotope of carbon, which is a carbon-12 isotope that they used. And the carbon-12 isotope has a couple of features, as we can see here. Now we can figure those things out. It has, in terms of protons, 6. It should also have, in terms of electrons, 6. And the mass number is 12, which means the number of neutrons should be 12 minus 6, which is 6 there. So it should have all of those sort of subatomic particles. It also has a mass of exactly 12.00 AMU. AMU is an atomic mass unit. So they use this isotope of carbon to compare everybody else to. There is a comparison from AMU and grams. So 1 AMU is 1.6606 times 10 to the minus 24 grams. All periodic tables use the atomic masses based on the carbon-12 isotope. So what they did, for example, is, they looked at hydrogen and said hydrogen is only about 1.11% as massive as the carbon-12 isotope. And they did a little math where they're like, okay, 1.11% converted to decimal times it by 12, and you get something like 1.008. They did similar sort of calculations for everything on the periodic table. And for example, there are sodium, 2299 for sodium there on the bottom. So what do these numbers mean? It basically, one way that you could refer to the atomic mass would mean that there are 1.008 AMU per atom. It could also say for sodium, there is 2299 AMU per atom of sodium, and so forth. Now, you may be thinking to yourself, well, if they use carbon 12 isotope as the standard to compare everybody to, and the carbon 12 isotope has a mass of exactly 12 AMU, why oh why, when I look at the periodic table and I take a peek over there at carbon, I don't see 12.00 even. I see 12.01. And that is because what we actually see on the periodic table is all the average values of all the naturally occurring isotopes for those particular elements. So when we look at the periodic table and we see that number on the bottom underneath the symbol, it's actually the average atomic mass. Although most people don't call it average atomic mass, they just call it the atomic mass. Also, not to confuse you at this point, but later on, we will actually go to that number and use it in a more convenient unit, which is actually molar mass, which are grams per mole. But right now, we're talking about atomic mass or atomic mass, which is basically AMU per atom. So because there are certain elements that have naturally occurring isotopes, we could actually calculate the atomic mass of an element by using a formula of atomic mass mu is equal to the percent of the first isotope times the atomic mass of the first isotope plus the percent of the second isotope. And by the way, when I say percent here, it's sometimes referred to as percent abundance, relative abundance. It's basically the percentage at which that particular isotope occurs naturally. Like, for example, you may have one isotope of an element that occurs 70% of the time. You may have another isotope of that particular element that occurs 30% of the time, adds up to 100%, right? so they don't occur at the same sort of rate, if you will, or amount, percentage. Let me just erase this here so I have a little more room. So we're going to take the second isotope's percentage, our relative abundance, times the, I was going to call it atomic mass m of the second isotope. And if you had a third isotope, you would follow the same path. If you had 4 isotopes, you would follow the same sort of pattern. The key, though, is people always, when they do this calculation, they want to multiply here, but it is adding. So that's an important thing to keep in mind. So, for example, if we look at, and by the way, we were talking about carbon. By the way, there's the carbon 12 isotope, which has a mass of exactly 12. There's also a naturally occurring isotope of carbon 13, occurs about 1% of the time or so, and the other one's about 99% of the time. And carbon 13 isotope has a mass of about 13.000, a bunch of zeros and stuff. So when we do this calculation for carbon, that's how come we end up with 12.01, like we see on the periodic table. It's also important to remember that although we think of the numbers on the periodic table as the atomic mass, they are average atomic masses. So, for example, carbon, as I just mentioned, has carbon 12 isotope, which is about 12 in terms of its mass, and carbon 13, which is about 13. If you were to grab out a carbon atom just by itself, you would never really find one with a mass of 12.01 like you see on the periodic table. You would either pull out a carbon 12 isotope or a carbon 13 isotope, which has the appropriate masses for each of those. So that's also something to keep in mind. So for example, here, if we look at the atomic mass of copper is 63.546 AMU. It exists as 2 isotopes, carbon 63 and carbon 65. Carbon 63 is more abundant and has atomic mass close to 63. And calculating the average atomic mass and adding them together will give us our atomic mass. So if we take a look at one here, here's our table, and here's our 2 isotopes. Once again, this is copper 63, and that is copper 65. Once again, that's the mass number, which is our top numbers here. Here is and this is their book symbol for AMU. And that is the atomic mass of copper 63. That's the atomic mass of copper 65. Basically, copper 63 occurs about 69% of the time, and copper 65 occurs about 30% of the time, 31% of the time. When you're given something like this, one thing that you do want to kind of take a peek at is the percentages, and you do want to make sure that it does add up to approximately 100%. It may be a little below 100%, maybe a little above 100% with rounding. But you definitely want to be in that ballpark of 100%. If you're not, then you probably have an isotope missing, or you got to figure out the percentage. And you can do that pretty easily by just subtracting from 100, right? So in order to have 100% of all the isotopes, you got to have 100. So you can subtract those percentages. So we're going to use our formula here to get to our atomic mass here. And again, our atomic mass for copper, put an M there, is going to be our first isotope. So we're going to take the percentage of our first isotope. So you could do one of two things with this. You do have to kind of convert it into a decimal. So you can move the decimal place 2 places to the left, which will give you 0.6909. And that's basically our 6909%. We're going to times it by the atomic mass of our first element, which is 62,928 AMU. Again, we're going to add it here to our second isotope. The other option, instead of moving the decimal place 2 places to the left, is you could take 3091% and divide it by 100%. And that basically will move your decimal place for you. Or again, you could just move the decimal place, whichever way you want to do it. But it basically gets you to the same spot. We then would times it by the atomic mass of our second isotope, which is this. And at this point, we'll do our math here. We're going to take 0.6909 times 62.928. We're going to add it to basically 0.3091 times 64.9278. And that is going to get us 63.55 AMU as our atomic mass. Most of the time when we do take that number off the periodic table, when you look at the number again on the bottom here, usually 4 significant figures is typically how many digits we take it to. And that's why, again, we would round to 63.55. So how do they figure out, the different percentages of the isotopes and the masses? They use something known as mass spec, or mass spectrophotometry, and mass spec for short. It basically runs the sample after it heats it up through a sort of electrical field and magnetic field. And it's sort of, in my bad example here, you send the sample through, you heat it up, it goes through like a magnet field and electrical field and kind of spins, and then it hits a sort of screen, and basically it separates it out based on where it hits it. So on the sort of picture, as you can see here, the heavier guys kind of come off later, and the lighter guys kind of come off earlier here, and you get different peaks that occur. And doing some calculations, they basically figure out, based on the size of those peaks off of the mass spec, sort of the percentages of each of those isotopes to come off. So that's sort of the way at which they are able to sort of figure out the percentages of these different isotopes. And also using a magnetic field, or a magnet, I guess is a way of saying that as well, and electrical field, they're able to sort of separate them out by mass as well. All right, so why don't you try one here? Silver exists with an atomic mass of 106.9041 and 108.9047. Determine the average atomic mass for silver if the percent abundance for each isotope is 51.82% and 48.18%. So respectively. So basically, this guy's a percentage. This guy and this guy goes together. And basically, this guy and this guy goes together. All right, so why don't you take a couple minutes there and see what you come up with. And we'll go through it. Okay, let's take a look at it and see what you come up with. So we have basically 2 isotopes of silver. So our first isotope here of silver, just going to put our guys together. So that's going to be 51.82%. And it will have a mass of 106.9041 AMU. Our second isotope here of silver has a percentage of 48.18%. And it has a mass of this guy here of 108.9047 AMU. Once again, we want to take kind of a peek here at our percentages. That's 48, about 52. So that's fairly close to 100%. So we're not really missing any isotope. So we can go and do our calculation here, if I can find the right thing to use. There we go. All right, so we'll do our atomic mass here. Taking our first isotope, once again, I'm just going to move the decimal place 2 places to the left to convert it into a decimal. 0.5182 times our 106.9041 AMU. Again, we're going to add, not multiply here. Our second isotope, once again, I'm going to also just move the decimal place 2 places. 0.4818 times our 108.9047. should be good at this point. So putting those guys into our calculator here, we got 0.5182 times 106.9041 plus 0.4818 times 108.7. That's going to give us, again, taking into about 4 significant figures, 107.9 AMU. Once again, if you take a peek on your periodic table for silver, and that's pretty much what you're going to see there on the bottom. So that's pretty good. All right, one last one here. Chlorine. Yes, the thing's got in the way there. I think that's chlorine. Chlorine exists as 2 isotopes, chlorine 37, 36.96590, and chlorine 35. If the percent abundance of each of the isotopes is 24.47% and 75.53%, what is the atomic mass of the chlorine 35 isotope? If the atomic mass of chlorine, average atomic mass of chlorine is 35.46. All right, take a few moments there and see what you come up with. Here we're actually looking for the atomic mass of one of the isotopes. So take a moment. Okay, let's take a look. So in this case, we got a little bit different. We know that chlorine 37 here has an atomic mass of 36.96 590 AMU. And it has an abundance here of 24.47%. We also know that chlorine 35 has an AMU of what we're looking for, but has a percentage of 75.53, or relative abundance, 75.73. We also see here, we'll use their number of 35.46 AMU is the average atomic mass. All right, so we do want to approach the same way. In this case, we actually know the average atomic mass, so that's going to give us 35.46 AMU is equal to our first isotope. And again, I'm just going to move the decimal place here. So that's going to give me 0.2447 times 36.96590 AMU. Again, that's going to be plus our second percentage. I'm going to move the decimal. I'm going to call it X, my unknown AMU. Call it X in this case. We have something to solve for. All right, so we're going to do a little bit of math here. I'm going to get a number here. So I'm going to take 0.2447 times it by 36.96590. And that's going to give me 35.46 AMU. And that'll give me something like 9.0455573 plus 0.7553x. I'm going to subtract this to the other side. So that will give me 35.46 minus the answer. That's essentially going to give me 26.41444. And guess it again, 427. AMU is equal to 0.7553x. We're going to divide this to the other side. 0.7553. That's going to cancel. And that will give us 0.7553. Going to give us something like, go right about there. X will equal 3497 AMU. So it looks like close here, 34. It looks like D would be our winner in terms of our answer in this particular case. Right. All right. So that obviously is something you need to be able to do, is calculate the atomic mass, like this particular example, maybe calculate the atomic mass of an individual isotope if you're given some other information, or even the percent relative abundance as well. Well, that looks like that should do it here for chapter 5. Thanks for watching. Have a good one. We'll see you on the next one. Hello there, and welcome to the end of the lecture. Hopefully, this was a good lecture for you. I know what you're thinking. We're here at the end of the lecture. This is usually our time for chemistry jokes. Today, we will do something a little different. I'm going to give you a riddle, and perhaps based on the knowledge that you've got from this chapter, maybe a periodic table which might be on a wall over there, you might be able to figure out this riddle. The hint is I like to eat it for breakfast. The riddle is 56, 27, and 7. Good luck and goodbye.